once again in the video lecture of communication engineering. In today's video lecture, we are going to discuss about the digital pulse modulation technique. In the last video lecture, we have discussed about the pulse code modulation, and today we will discuss its some more different types of digital pulse modulation technique, that is differential pulse code modulation, delta modulation and adaptive delta modulation. Before that, we will understand one more concept related to the pulse code modulation, that is compending. So, let us start. Compending, what is the meaning of compending and why it is required in pulse code modulation or in digital modulation technique? What is the role of this compending? Compending, as the name indicates, it is a combination of two words, that is the compression and the expansion. Compending is a technique of achieving non-uniform quantization. In the case of non-uniform quantizer, we have seen for the signals like voice signals or the speech signals where most of the information lying near to the 0 level, we require more number of levels, and to the higher values we require less number of levels. So, we can opt non-uniform quantizers. But non-uniform quantizers are quite expensive. So, what we can do for such kind of signals, there is an alternate of non-uniform quantizer, that is called compending. Compending is a technique with the help of which we can obtain the results of non-uniform quantization. The process of compending is the compressing of the signal in the transmitter and then expanding the signal in the receiver using same nonlinear scale in order to reduce the noise. Voice signals are more likely to have amplitude near 0 than at extreme peaks, as we have discussed in the last case of non-uniform quantizer also. So, for such signals with non-uniform amplitude distribution, quantizing noise will be higher for amplitude value near 0, and non-uniform quantizers are expensive also. So, if we want to quantize speech signals or voice signal, then instead of using non-uniform quantizer, what we can opt? We can opt compending technique. What are the blocks of compending? In the compending, first we will have compressor at the transmitting side, then the compressed signal will be passed from an uniform quantizer, and then the information will be expanded with the help of an expander at the receiver side. So, what this compressor will do, this compressor will reduce or will attenuate the signals at the higher amplitude value, and expander, what it will do, it will increase the gain of higher amplitude signals. So, through compending, what we can do, we can increase the amplitude of speech signals near to the 0 level. Okay. The higher amplitude of the voice signals are compressed prior to the transmission, and then they will be expanded in the receiver. So, in this way, what we will get? We will get the digitization of input signal with the help of compending technique and at lesser cost in comparison of non-uniform quantizer. Now, the question comes, how we can perform this compending? There are two laws with the help of which we can perform compending. The first one is the mu law and the second one is A law. Mu law is generally followed in US, North America and in Japan, while the A law is followed in the Europe or in some another countries. The standard and the specification of mu law compressors are, this is the expression with the help of which we can perform the compression of the signal that we want to transmit. In this expression, ln, that is the ln 1 plus mu x divided by ln 1 plus mu, where mu is the degree of compression. This particular law is used in North America telephone system. Soft voices actually gets amplified while strong voices are suppressed in case of compressor. What we will do in compressor, we will attenuate the higher amplitude signals and we will increase the or amplify the signals having lower amplitude. Okay. The ALO, this is the expression for ALO. These are the two expressions with the help of which we can perform ALO compression, according to which AX divided by 1 plus ln of A for x lying between 0 to 1 by A. If x is lying between 1 by A to 1, then the expression will become 1 plus ln AX divided by 1 plus ln of A. Okay. This particular law, A law of compressor, is used in Europe and the follower of the Europe country. Here we have the characteristics of the compression with the help of mu law and with the help of A law. The first figure is indicating the compression characteristics of mu law, and the second one is indicating the compression characteristics of A law. Here we can observe, here this m and here this A is the variable, that is the parameter that we have seen here also, that is the degree of compression, mu and A, capital A. So here what this particular curve is indicating, the amplitude of lower level signal is increased or amplified, while the amplitude of higher value signal will be attenuated. The reverse of it will be performed at the receiver with the help of expander, with the help of expander, and we will get our signal. In case of ALO, this degree of compression is varying, which is followed in Europe and other countries, followed of the European countries. Here also the amplitude of lower level signal will get amplified and the amplitude of higher level signals will be attenuated. This particular technique of compression and expansion is used for those signals where most of the information lie near to the zero level. This compression and expansion we cannot apply for each and every signal. Okay. The next digital pulse modulation technique is differential pulse chord modulation. In the last video lecture, we have discussed the bandwidth requirement for the case of PCM system, that is NFS. Minimum bandwidth required for the transmission of PCM signal is equals to N into Fs, where N is the number of bits and Fs is the sampling frequency. Then what is DPCM and why it is used? DPCM stands for Differential Pulse Chord Modulation. We can say it is a kind of modification of pulse chord modulation technique. What we were doing in the case of pulse chord modulation, we were converting analog signal into a digital signal with the help of sampling, quantization and encoding. When we were performing encoding after quantization, then each quantized level will be encoded with a different binary set. Okay, that means in case of pulse chord modulation, what we will do, each sample and each level will be assigned with some binary. In differential pulse chord modulation, what we will do, it is also a technique of converting analog signal into digital signal, but in the case of differential pulse chord modulation, analog signal is sampled and then the difference between the actual sample value and its predicted value. What is predicted value? Predicted value will be based on the previous sample. Okay. The difference, what we will do in case of differential pulse chord modulation, in case of differential pulse chord modulation, the analog signal is first sampled and then the difference between the actual sample value and its predicted value is quantized and then encoded. That will provide us a digital data. Here in case of DPCM, rather than assigning binary to each sample, the difference of two samples will be considered, that is the current sample and its the previous one, that is the predicted one, and their difference will be encoded into a digital signal. Okay. So, DPCM code word represents difference between samples, unlike PCM where each code word represented a sample value. So as we can understand from this fact, if we are assigning binary or if we are encoding the difference of the two samples, then the number of bits required or the total number of division required to represent each sample will be reduced. This will help us in reducing the bandwidth requirement. So basically DPCM is used to reduce the bandwidth requirement. The bandwidth requirement of PCM is very high. So to deal with this problem, we can use differential pulse code modulation. So let us understand about the DPCM in detail. That we have seen why we require DPCM. Let us discuss with the help of this graph also. So the sample of an analog signal are highly correlated with each other. What is the meaning of the word correlation? The samples of any signal are very similar to each other. Correlation means similarity. If we will sample some analog signal and our sampling rate is high, then one sample at a particular time instant and the next sample near to that, there will be much similarity between these two samples. Let's say T1 and T2. Okay. So the samples are highly correlated to each other. Correlated means they are very similar to each other. That means they may contain the similar amount of information. So how this will help us in reducing the bandwidth? The signal's value from the present sample to the next sample does not differ by a large amount. So the adjacent samples of the signal carry the same information with a very small difference. So what we can do, when these samples are encoded by the standard PCM system, the resulted encoded signal contains some redundant information bits. What is the meaning of this redundant information bits? We will discuss. The sample are quantized to the nearest digital level as shown here in this particular figure with the help of these two small circles. So in this particular figure, what we can observe at 4 TS, at 5 TS and at 6 TS, these three samples are containing the same information 110, 110, 110. So if we will transmit or if we will use pulse code modulation technique, then we have to assign or we have to encode each of these three symbols with 110, 110 and 110, and then we have to transmit three of them. But if we'll use differential pulse code modulation technique, then what we can do, we can consider the difference of the two adjacent, the first one and its predicted value, sample, and then encode that particular difference or quantized that particular difference. So it will help us in reducing the number of bits required to represent that particular sample. That means, what is the meaning of this thing? If the samples or if the information in the different sample or in the adjacent sample is same and we are transmitting the same information again and again, that will increase the redundancy. This is called redundant information bits. The information contained in 4 TS, 5 TS and 6 TS can be carried by only one sample because three of them are equal to each other. That means three of them are carrying the same information. So rather than sending the same information by three different samples, we can transmit it by with the help of only single samples, but three samples are carrying the same information. This is called the redundancy. So with the help of this DPCM, what we can do, we can decrease, we can reduce this redundancy. It will help us in decreasing the number of bits required to encode and then to transmit the signal because it will help us in reducing the quantization level. So it will help us in reducing the number of bits that will further help us in reducing the bandwidth required for the transmission of the data. So let us check with this with one example. Here we have analog signal that we want to convert into digital signal and then transmit. So first this analog signal will be sampled. Okay, here we have the digitized PCM signal. Digitized PCM signal is what? First we have sampled this signal in the time axis, then we have sampled this signal in the magnitude axis, and then each level is represented with number of bits. Each sample is assigned with a different code word. This is the simple PCM system. In differential pulse code modulation, what we will do, we will consider, let's say this is the T1 and this is the T2. Rather than considering these two different samples, what we will consider the difference of these two samples. Similarly, then we will consider the difference of the next two samples, that is the current sample and its predicted value. So what if it is, let's say it is of 0.5 and this is of 0.3. So 0.5 minus 0.3 will become 0.2. Here what is the maximum amplitude level that for which we have to select the quantization level is 0.5. But after taking the difference of these two, it will become 0.2. Okay, so now we have to decide the number of levels according to the 0.2 magnitude level. Obviously, the number of levels will be reduced. If we want to select the number of levels from 0 to 0.5 or from 0 to 0.2, obviously the number of levels required will be lesser in this case. If the number of levels required to quantize the signal will be lesser, then the number of bits required to represent each level will also be reduced. Here we have the differential pulse code modulated signal. What we have considered, instead of quantizing and encoding each sample, first we have considered the difference of the samples. So the higher or the highest magnitude level will be decreased, and now we can represent each level with only 2 bits rather than 3 bits as in the case of PCM signal. So what output we are getting from this differential pulse code modulation? We are getting reduction in the number of bits required to transmit the information. If the number of bits will be lesser, then obviously the bandwidth requirement for transmitting the signal will be lesser. Okay. So what is the principle of differential pulse code modulation? If the redundancy is reduced, redundancy is what? Similar amount of information carried by multiple samples or the adjacent samples. Rather than saying multiple samples, we can use the word adjacent samples. If the adjacent samples are carrying the same information, that is called as the redundancy. So if the redundancy is reduced, then the number of bits required to transmit one sample will also be reduced. So this type of digital pulse modulation technique is called differential pulse code modulation, where in the DPCM works on the principle of prediction. The important thing in case of DPCM is prediction. Okay, the value of the present sample is predicted from the previous sample by considering high correlation between the samples. Okay, the prediction may not be exact, but it will be very closer to the actual sample value. So this is the basic principle with the help of which we can reduce the number of bits and we can reduce the bandwidth requirement for the transmission. Here we have the DPCM transmitter block diagram. First we will have the sampled input signal, then we will have a quantizer, then we will have a predictor. The main role of in DPCM is of predictor. This predictor will help us in predicting the current sample value from its past value. This may not be exact, but will be very much closer to that particular value because of high correlation. Okay, so what we will get at the output? We will get the digitized signal. So here in case of DPCM, after this the output will be encoded. the quantized output then will be coded and we will get the digital output. Okay, so here we have some equation with the help of which we can discuss the working of this particular DPCM transmitter. The sampled signal will be indicated with X and TS. Here the projector output will be indicated with X cap and TS. Here we have a summer that will provide the summation of this quantized output and the predicted output. So it is UNTS, that is the input of the predictor. It will help us in predicting the current sample value from its past information. So finally what we will get the amount or the level of quantization with the help of this, and then the bits will be encoded and we will have our digital information that we can transmit with lesser number of bits. The after DPCM, the next digital pulse modulation technique is delta modulation. In DPCM, what was the main benefit? We were able to reduce the amount of bandwidth by reducing the number of bits required to represent each level, by decreasing the quantization levels, by taking the difference of current sample and its predicted value. Okay. So what we were doing, we were actually reducing the total magnitude of the information that we are required to quantize in the magnitude axis or in the amplitude axis. What is delta modulation? It is very much similar to the differential pulse code modulation, but here the each level will be represented with the help of only one bit, either 0 or 1. Rather than assigning number of bits to a particular level, the each level will be indicated or will be represented either with bit 0 or with bit 1. Let us understand the concept of this delta modulation. Delta modulation we can consider as a special case of differential pulse code modulation, and it is also called as 1-bit version of DPCM. In DPCM scheme, if the baseband signal is sampled at a rate much higher than the Nyquist rate, that is, if Fs is much greater than twice of Fm. That means if the samples are very much closer to each other, then the correlation between them will also be higher. That will help us so that the quantized signal will contain all the information about the original signal. Okay. So if in DPCM scheme, if the baseband signal is sampled at a rate much higher than that of the Nyquist rate, purposely to increase the correlation between adjacent sample of the signals, so as to permit the use of simple quantizing strategy for constructing the encoded signal. Then in case of delta modulation, what we can do, it is a 1-bit PCM code to achieve the digital transmission of the analog signal, and only 1 bit is required to represent each level, that is either 1 or 0. That is why it is called 1-bit PCM or 1-bit DPCM. Rather than a single bit PCM, it is more oftenly known as 1-bit DPCM. Logic 0 is represented when, or logic 0 is transmitted when, if the current sample is smaller than the previous sample. What we will do, here also we will consider the difference between the adjacent samples, and 0 will be transmitted if the current sample is smaller than the previous sample. Logic 1 or bit 1 will be transmitted if the current sample is larger than the previous sample. For example, let us take this particular example. So if we want to transmit with a help of delta modulation, we are considering, for example, this one. If this particular sample is, if we will compare this sample with this sample, 2Ts with Ts, then the value of 2Ts is greater than the Ts. Then the difference of them will be transmitted with the help of bit 1. Okay. Now we will take the difference between, let's say, this one and this one, this one and this one. That then this is our current sample, this one is the previous sample. The difference between them obviously negative, the current sample is lesser than the previous sample, then corresponding to the difference between these two will be transmitted with the help of binary 0. The difference between them, between these two samples, will be transmitted with the help of binary 1. Only one bit is required to be transmitted in case of delta modulation, depending upon whether the difference between the current sample and its previous value is positive or negative. So obviously in case of delta modulation, the bandwidth requirement is least in comparison of all the digital pulse modulation technique. Here we have some more features about the delta modulation. First of all, we have to perform the oversampling. Fs must be greater than much greater than twice of Fm. And oversampled input is taken to make full use of the signal correlation. This difference we can consider only when the samples are very much near to each other and they are highly correlated to each other. If the correlation between the samples will be lesser, and will take the difference between them and then will transmit them after quantization and encoding, they may not contain all the information regarding the main input signal. So this is an important thing, over sampling, to increase the correlation between the samples. Okay. Then the quantization design is simple in case of delta modulation, because here we don't require encoder. If the difference is positive, it will be transmitted with binary 1. If the difference is negative, it will be transmitted with the help of binary 0. The input sequence is much higher than the Nyquist rate. That is again the case of oversampling. The quality is moderate. Obviously, if we are transmitting only one bit, then we again, when we will convert that digital data into the analog information, the quality will be slightly lesser than DPCM and PCM. The highest quality we will get in the case of pulse width modulation. The design of the modulator and the demodulator is simple. The staircase approximation we will get in the output. The step size is very small in case of delta modulation. So here we have the block diagram of delta modulator, 1 bit quantizer, a delay unit and the oversampled input signal. So here we will have the oversampled input signal. It will be quantized with the help of 1 bit quantizer. Here we don't require any encoder. Here we will have the delay unit. What this delay unit will provide? It will provide the previous value of the previous sample, that with the from which we want to consider the difference of the current or existing sample. It will be indicated with X, cap and TS. Here we don't require predictor. Here we require a delay unit that will provide the value of the previous sample. And at the output, what we will get? The difference of these two can be either positive or can be negative. That is the current sample value and the previous value. If the difference is positive, it will be quantized with binary 1. If the difference is negative, it will be quantized with binary 0. So simple to transmit. So its modulator and demodulator is very much easier to design. And here we require least transmission bandwidth. Okay, that is the main benefit of delta modulation. So these are the two advantages, 1 bit quantizer and very easy to design. But in case of delta modulation, we have two severe disadvantages, that is called as slope overload distortion and granular noise. These two noises occur in case of delta modulation. What are these two noises? The step size will remain constant in case of delta modulation. Here, in case of delta modulation, the step size will remain constant. If we will fix the step size too small or too large, then these two noises may occur. if the step size we will consider is small, then slope overload distortion may occur. If we will consider this step size too large, then granular noise may occur. What are these two noises? Here, if this is the analog signal that we want to sample, quantize and that we want to sample and quantize to convert into a digital form, and we have considered this step size. This staircase approximation we are getting after quantization, and if this is the step size, here what is happening, our information is varying quickly, but because we have fixed the step size and this is the step size which is very small, it may not be able to follow the information, varying information, and what we will get at the output, we will keep on getting the same output of the output of, from the delta modulator. What should happen? As our information content is varying, the output should also vary. But because of a small delta size, we will keep on getting the same output. This is called a slope overload distortion. Now, if we have considered the step size too large, consider this particular portion where the information content is constant, there is no variation in the information, but we have considered the step size too large, then it will keep crossing the information. That means what we will get, we will keep on getting variation in the output. The output should remain constant as our information is also not varying, but we will get variation in the output from the delta modulator because of large step size. It is called granular noise. What is when slope overload distortion will occur? It will occur if the step size is too small. It will not be able to follow the variable information. The output must change, but it will remain constant. Then the slope overload distortion will occur. When information content is constant, we want to there should not be any change, there should not occur any change in the output, but it is occurring because of large step size, then this particular kind of noise is called as granular noise. So, these are the two disadvantages of delta modulation that we can remove with the help of next technique, that is adaptive delta modulation. As the name indicates, it is adaptive delta modulation. Adaptive word indicates it will adapt the change in the information, and in case of adaptive delta modulation, we instead of having a fixed step size, what we will have a variable step size. The step size of the staircase like structure will vary according to the variation in the information. It is adaptive to the variation in the information. So, in order to overcome the quantization error due to the slope overload and granular noise, the step size is made adaptive or variable to the variation in the input signal. Particularly in the steep segment of the signal, the step size is increased when our information is varying quickly, and the step size is decreased when the input is varying slowly. So, this method is called as adaptive delta modulation. So, let us quickly check the transmitter and its representation. Here we have the adaptive delta modulator. All the components are same as we were using in the case of delta modulation. Only one more block is added, that is logic for step size control. How this logic will work? Here we have the same information that we want to transmit, okay, but here as the information content is varying, this slope is varying, the step size we can observe is also varying. Where the information content is varying slowly, then we can observe this step size is also reducing. So, how we can increase or decrease the step size? There is a rule with the help of which we can understand the variation in the step size. The logic for the step size control is added in this diagram. The step size increases or decreases according to a specified rule depending on 1-bit quantizer output, depending on this output. How? For example, if 1-bit quantizer output is high for the first time, if we are getting output is equals to 1, then the step size may be doubled for the next samples. What if the difference between these two is positive and we are getting 1 here, binary 1. So the step size for the next sample can be doubled or can be tripled. If this difference is negative and we are getting binary 0 at the output, if 1 bit quantizer output is low, then the step size may be reduced to 1 step or half of the previous one. So this kind of logic control will be applied in case of adaptive delta modulation, and the step size will vary according to the variation in the information content. So in this way we can deal with the problem of, or we can minimize the granular noise and the problem of slope overload distortion. Okay. So in today's video lecture we have discussed about the compending, that is the compression and expansion of the signal, that is an alternate of non-uniform quantizer. Then we have discussed differential pulse code modulation, where we can reduce the number of bits required to represent each level. That will further help us to reduce the bandwidth requirement for the transmission of the signal. Then we have discussed the delta modulation, where we require least transmission bandwidth in comparison of all the digital pulse modulation techniques. Then we have discussed the problems that can occur in the case of delta modulation because of the fixed step size. Then we have discussed the adaptive delta modulation, where we can apply the logic of variable step size that will help us in reducing the noises that can occur in the case of delta modulation. So this is all about this video lecture. Thank you everyone.